Welcome back, folks. This is lecture number 5 in our discussion of programmable logic controllers. Today, we're going to continue our discussion of combinational logic. Before we start, let's take a trip down memory lane. All right, this should look familiar, and you should still be able to solve it. If you do, I suspect your opening move would be to put a box around these components. And whether you do that mentally or whether you physically do it, you do it. You take the entire problem and you shift your focus to a very narrow part of that problem. And you would say, well, the R box here is that 200 in parallel with 100, which is about 67 ohms. Then you would redraw the circuit with the 50 ohm that was originally there and your new 67 ohm resistor. And you might use a voltage divider where you said the voltage of interest is the resistor of interest over the total series resistance multiplied by the source. Plugging in our values, we say that the voltage out is equal to that combination, so this resistor right here. So that is 66 ohms over 50 plus 66 ohms multiplied by the source voltage, which gives you a voltage output of approximately 5.7 volts. Not too complicated, but once again, you had to focus. You had to take the entire problem and you had to narrow it down. You put those parallel resistors together, you redrew the circuit, and then you use the voltage divider. So multiple steps, each one very simple in and of itself. I would argue that that's the same problem we face with our programmable logic controllers. For example, you might walk up to a machine and that machine has many, many functions, but you don't focus in on the entire machine. You break it down into pieces. You break it down into very little pieces, pieces that you can focus on, pieces that you can understand, and then you move from one to another. You don't want to get lost in the forest of rungs, right? Too many rungs in that ladder logic. But you can understand what happens on an individual rung. That is our focus of this video. We're going to talk about applications of combinational logic. We're not going to talk about circuits that have memory. For example, you won't see the seal in or the latch in this particular lecture. We're going to explore the operation of a few machines. And we're also going to use user-defined function blocks, admittedly as something magic, something that allows us to take what we don't want to deal with and push it off to the side and deal with it another day. Another way of saying that is we abstract. And that is a valid thing we can do because the IEC 61131-3 code upon which our Micro800 is programmed allows us to do that. It allows us to layer our code. And I think in one of the previous videos I said it was like an onion. It's layers of abstraction. Let's define a few terms that might be useful to us. The first one is permissives. You could think of these as prerequisites. You could think of these as conditions that must be true for a system to function. So that is permissives. We also have the concept of a trip. And these are things that will stop a process that's already in motion. You could think of trips as maybe a fault condition. By the way, we have to be careful when we talk about fault conditions. It's one thing to say, well, if the machine is malfunctioning, you mash the emergency stop button, the machine comes to a complete stop and life is good. But not all processes are so simple. As an example, you could consider a machine that's lifting a weight, and you can imagine a situation where somebody is underneath that weight. And if you were to hit an emergency stop, the weight might actually fall, causing additional injuries to that particular person. So a fault condition is very specific to the machinery on which we're talking about. We have talked about trips before, and that was in dealing with the motor starter. So let's sketch that out really quick. This is the basic circuit for our three-phase motor. We have a circuit breaker in the front. We have the primary contacts from our motor starter. There may be an auxiliary contact here as well. You recall these are the heaters. And on that overload block, there will be another contact. So this one here is what I'd like to draw your attention to. This is the overload contact. You remember how that's hooked up on the PLC. We have our output block. So here's a terminal. We have that overload contact, and then you have the coil for the motor starter. So this is the motor starter coil. And we said this is the overload contact. And we can let this be output 0, 2 on the PLC. Recall that if the motor experiences an overload, these heaters will give off heat. And not shown on this particular diagram, there's bimetallic strips. Those will bend, and if they bend far enough, they will actually trip this contact. Right? It's a mechanical trip, like a spring-loaded lever, it trips. When that occurs, it opens this overload contact. The trip of the overload block opens the overload contact, disabling the coil. And as soon as the coil is disabled, we lose the main contacts and the motor stops. So it's a trip. Something that was running is tripped. I suppose you could make the argument that this is a permissive, because after all, the motor will not start if it's tripped. Although that doesn't seem right, does it? In which case, we'll call this a trip. At this point, I would like to go over a few examples. Let's suppose you have a valve, and we'll call that a motor-operated valve, M for motor. We have a pump, and we have another motor-operated valve. And our objective is to move some fluid from one place to another. This motor-operated valve has contacts. It has a valve open contact, and it has a valve closed contact, as does its mate on this side. We'll call this the suction valve, and we'll call this the discharge valve, with the objective of moving fluid in this direction. Right? So we open the suction valve, we open the discharge valve, and then we can activate the pump to move the fluid. Now, something you should know, a motor-operated valve takes a certain amount of time to operate. You could consider it a rising stem valve. And a rising stem valve, the valve stem will come up like so. And what you do is you put little switches, you put micro switches there. So as the valve is closed, it's on this stop right here, and we call that closed. As the stem rises, it'll come up and it'll touch this switch, and we'll call that open. So here we are open, here we are closed. Here we are opening, now we're open, now we are closing, and now we are closed. For clarity, let's put that into a table. So we're going to call this the state of the valve. Our states were closed, opening, open, closing, and closed, back where we started. When we are closed, the closed contact is true, the open contact is false. When we are opening, they are both false. When we are open, the open contact is true. When we are closing, they are both false. And when we are closed, we're back where we started. The closed contact is true. The open contact is false. For this example, let's say we need an indicator lamp, and that indicator lamp has to tell us that the motor-operated valve is active. So we have a suction valve and a discharge valve. And what we want to know is the valve in motion? Or better put, is either valve in motion? So when they're both closed, the light will be out. When they're both open, the light will be out. But if they're moving, the light will be on. Let's start with the input block to the PLC. So in block, we'll add the switches like so. And we'll call this MOV1 open, MOV1 closed, MOV2 open, and MOV2 closed. And if we were to put this into our program map, program in map, we would map those to a Boolean MOV1 open, a Boolean MOV1 closed. We said our objective was to make some ladder logic. I think we've got enough room here. In the end, we want a lamp. We want a coil. We'll call this XMOV active. Again, where the X represents a Boolean value. We know there are 4 contacts that we need to address. Okay, and now we can consider what's going to happen to the lamp. As it's drawn here, what would happen is if all of the switches were closed, the lamp would come on. And that's physically impossible because you can't close the open and you can't close the closed at the same time, right? So that's physically impossible. But again, that's not what we wanted anyway. Instead, what we want is a condition where if none of the switches are closed, our active light comes on. So let's go back to this. So we want a condition where none of the switches are closed. That implies that the valves are opening or closing. And if we were to look at this, we would say our Boolean algebra would tell us that this is D naught, C naught, B naught, A naught. That's the operation. This is a NOR gate. The truth table, or at least part of it, looks something like this. So 0, 0, 0, 0, 1. So when none of the switches are active, right, when they're all zeros, we get a 1. And for every other entry, we get a 0. If you want, I'll leave it to you to fill in the rest of the table. Let's look at this again. So we started with a description of a system, a fairly large system, and we focused in on a very small part of it. And in that very small part, we came up with a rung of ladder logic that described one piece of it. So we now have enough information to light a panel lamp if any of the valves are in motion. While we're here, let's do another example based on this particular system. Let's draw a picture of the control panel. So we have a switch here, and we have a push button. The switch has 3 positions. There's manual, off, and auto. And the push button is labeled bump. Or if you prefer, we could label that jog. And what we are going to do is if we're in off, the system is off. If we're in manual, we can run the pump by pushing the jog button. If we are in full auto, the system will take care of itself and it'll turn the pump on and off as necessary. Let's capture what we know about this system. We have some inputs. So these are a magic thing called function block auto. At this point, we're just going to abstract this away. Somehow auto works. We're not going to address it now, but it works. And that will have an input into our particular system. We have a button, we have a switch for auto. We have a switch that will activate when we're in the manual position. We have the push button called jog, and we have the suction open indicator and the discharge open indicator. As for outputs, we have a Boolean for pump motor starter. Let's capture the behavior of our system. If we are in auto mode, we shall activate the motor starter whenever the function block demands. Again, that's up here. It's a little bit of magic happening for us, but whenever that block needs the pump to run, it will run. That is, assuming both the suction and discharge valves are open. If we are in manual mode, we'll activate the pump's motor starter when the jog button is pushed, right? So if we're in manual mode, we'll activate the pump when the jog button is pushed and both suction and discharge valves are open. Finally, if we're in the off position, secure the system. We're off for all other conditions. Let's see if we can convert this into ladder logic. I'm going to get rid of this last line just to give me a little more space, though. So we'll start here, and we'll call this the Boolean auto switch. All right, so if we are in auto, that will be true. We'll put the magic function block right here, and that would certainly have more logic in it, but whatever that logic is, at some point it will output a line that will say enable the pump. If the suction valve is open and the discharge valve is open, we can activate the motor starter. So this is X, what do we call that? Pump. We'll just call it Boolean pump. If we're in auto, this evaluates true. If the function block demands, this will evaluate true. If the suction valve is open and the discharge valve is open, we will turn on the pump. This entire rung will evaluate as true. But what about the second part? If we are in manual mode, and if we are to jog the system, and the suction valve is open and the discharge valve is open, so there's jog and both suction and discharge valves are open, then we activate the pump. So there it is. We had 1, 2, 3, 4, 5, 6. We had 6 entries into this system, and we are able to do it in one rung of code with one branch. That branch is for this OR when we want to use it in manual. I think it's useful to put this into a gate level representation, mostly so we can see how the individual pieces fit together on the ladder logic. This is Boolean auto. This is the magic from our user-defined function block. This is the manual. And this is the jog push button. So all of those, correction, if we're in auto and there's demand from the function block, this will be true. If we're in manual and we push the jog push button, this will be true. If either this condition or this condition is true, this will be true. From there, we add an AND gate. That AND gate has two inputs, and they are the suction, open, and the discharge, open. I think this is constructive because if you work the logic gates and then you have to force yourself to figure out where each piece is, I think it adds a little bit to the ladder logic. For example, this piece right there, piece number 1, is right there. Piece number 2 is here. Piece number 3 is the OR gate. That's this right here. So there's piece 3. This last piece with that AND gate is right here. It's a 3-input AND gate with inputs here, here, and here. Let's look at another example. For this example, we'll look at the UV light that's installed in a water treatment plant. So we have a channel here. Into each channel, we have a series of ultraviolet lights. And what will happen is you'll have the effluent is flowing this way, and as it passes those lights, shown here in green, it will be disinfected. So this is the side view. And you could think of the water level right there. Into this system, we're going to install 3 sensors. This is highly simplistic, but it will work for our purposes today. Our system now has some inputs. It has Booleans for each sensor. And we're going to have some output indicator lamps. We're going to have a caution lamp. We're going to have a fail lamp. And we're going to have an all is good lamp. The behavior is described. We'll have a fail if 2 or more sensors. Okay, so a fail is defined as the loss of 2 sensors. We have a caution if loss of 1 sensor. And everything is good if all sensors. For this first line here, you could consider that a majority vote. We assume that the system is overbuilt. It's built such that loss of 1 of the 3 UV banks would still let the system operate. This system isn't too big, so I think we can do a truth table. We'll add the outputs fail and caution. Each sensor can take on different values. Okay, let's complete the truth table for the fail. And we defined a fail if we have 2 or more sensors fail. So in this, the 0th row, we have 3 failures. So that's definitely a fail. In the the 1 row, we have 2 failures. In the 2 row, we have 2 failures. Finally, now in the 3 row, we actually have 2 sensors that are operational. So that is not a failure. In the 4th, we have 2 failures. Here we have a single failure, and now here everything is good. Now we can fill out the caution part, and we defined caution as a failure or loss of 1 sensor. So that's 2 sensor loss, 2 sensor loss, 2 sensor loss. There's 1 sensor failure there. There's a 2 sensor failure there, a 1 sensor, a 1 sensor, a no sensor. By the way, you notice I was calling this the 0th row, because if you were to look at it, this number right here in binary, so 0, 0, 0 is a binary 0. And 1, 1, 1, that's a binary 7. If you wanted to get really fussy, we would say that 1, 1, 1 base 2 is equal to 7 base 10. At this point, we can construct our ladder logic. We'll start with the fail first. And I'll put everything from Boolean C into this column, everything from Boolean B into this column, everything from Boolean A into that column. So the first line said that if all three sensors fail, right? If all three sensors fail, we are going to have a fault. So that takes care of that line there. The next one says if C and B fail, but A is good. So if C fails, B fails, but A is good, we still have a fail. Again, when we say A is good, that means this contact will close. That takes care of that line. The next one says if C is a fail, B is good, but A is a fail. So C failed, B is good, A fails. You might notice we are walking down a diagonal here. So the next one would look like this. C is good, B has failed, A has failed. That completes this diagonal. Okay, so we go back here. That must be this row here. We see C is good, B fail, A fail. By the way, Dahlin failed because that should have been a 0. If all the sensors are good, you shouldn't have a failure. Okay. We can move on to do the caution. So Boolean caution. The caution will activate if there's a failure of C. There will be a caution if C is good, B has failed, A is good. There will be a caution if C is good, B is good, but A has failed. You see the pattern there. We're walking down this diagonal. Let's see. That takes care of that one, and that one. The last piece of code is for the Boolean good. We'll write a true if all three of these evaluate as true, which is to say there's a 1 value for each sensor. When I made these notes, I thought it might be a good idea to sketch this drawing here, but the more I think about it, maybe not. But there you can see it if you like. So you're looking at a sum of products in logic gates. You can see there are 4 AND gates and 1 4-input OR gate. You could consider that a 3-input AND gate. That's a 3-input AND gate. That's a 3-input AND gate. That's a 3-input AND gate. And this piece here is a 4-input OR gate. Again, there you've got, let's see, we can get that into the camera. There's your 4 3-input AND gates and 1 4-input OR gate. We would call that a sum of products. While I've got you here, why don't we take a look at this circuit and let's see what it means to simplify logic. So we're going to start with a Carno map. And since this is just the demo, I'm going to walk through the steps very quickly without explanation. So Carno Map has a grid with these values printed across the top and these on the side, where this corresponds to Boolean C, and the first one here corresponds to Boolean B, and this one to Boolean A. If we take the values from the truth table, they are 1, 1, 0, 1, 1, 0, 0, 0. This is for the fail circuit. So you could look at it this way. Here, this cell is associated with 3 zeros. This cell is associated with 2 zeros. This cell has 2 2's, so it's not considered a failure. This cell is associated with that 0 and that 0. Anyway, without explanation, a Carno map would have you circle adjacent cells. And then it would have you claim that there's a simplification to this. This, for example, is B naught, A naught. This piece is C naught, B naught. And this piece here that walks across, because you could think of it as a loop that loops back on itself, is C naught, A naught, which gives us a Boolean expression of C naught, A naught, or B naught, A naught, or C naught, B naught. From there, we could construct ladder logic. So here, this is the Boolean C, so C naught, A naught leads to fail. This one is B naught, A naught is a failure, and this one is C naught, or excuse me, C naught, B naught leads to a failure. I will tell you that this circuit, where we have, this is the Boolean B column and this is the Boolean A column, this circuit is 100% functionally equivalent to this circuit. They will do the exact same thing. In our first circuit, we had we had 1, 2, 3, 4, 3 input AND gates, and this is an OR gate. And here we had 1, 2, 3, that's one less, and there are only 2 input AND gates and a 3 input OR gate. So it is considerably simpler. If we go back to this circuit, we could make a statement that this responds to 0, 0, 0. Right? So that's what this first line does. This second line responds to 0, 0, 1. The third to 0, 1, 0. And this fourth one to 1, 0, 0. Okay, keep that in mind. This one, a little trickier. So the first rung here will respond to 0, 0, 0 or 0, 1, 0. You'll notice there's nothing associated with B here. That first line doesn't care what B is, so it'll accept 0, 0, 0 or 0, 1, 0. This line will evaluate true if it's 0, 0, 1 or 1, 0, 0, because there's nothing in the C spot. This last one will evaluate true if it's 0, 0, 0 or 0, 0, 1, because there's nothing in the A spot. Just to recap, these two circuits, this one and this one, are functionally equivalent. We equated them using this Carno map, which I didn't bother to give you any real directions on how it works. We said this circuit is considerably simpler. It has one less branch, and each branch has one less contact. However, all things considered, I would recommend against doing such a thing. From a memory perspective, there's no advantage whatsoever because the PLC has considerable memory. It's decimal dust to try to mess with this type of simplification. And I would also argue that over the life of the equipment, this is a much easier thing to look at. So I might look at this 5 years from now and say, oh, okay, well, there's the C's column. All the things C related are there. There's the B's, there's the A's. Easy. You can see patterns such as this emerge, like those diagonals. If something goes wrong, you just don't have to think about it very much. You can come here and you look at it and instantly you can see what A is doing. Whereas this one here, you have to think about it. You have to mentally put these conditions in. Again, maybe you can do that in your head very easily, but for most folks, I suspect this is much better. Anyway, the Carno map exists. It certainly can be used. There was a time when it would make sense to do this. For example, if you were using all of those ice cube relays, this would allow you to save relays. You could make your panels smaller. You could make them use less electricity. But that is gone. Modern PLC, it's just not necessary. Don't be clever. Work for consistency and work for clarity. I'd like to do one more example. And this time, let's assume we're dealing with a diesel engine. This diesel engine has thermocouples. So we're going to add 4 thermocouples, and we're going to measure the exhaust port temperature for this particular diesel. We're getting a little bit ahead of ourselves, but I think that's all right, because this is a good time to tell you that the PLC accepts analog inputs. For example, you might have some twisted pair wire going off to a sensor, and that sensor would be bolted or screwed into the exhaust port of that engine. So again, this is an analog sensor. As far as the PLC is concerned, we have a ladder logic. We're going to create a function block called pyro, because that's what those exhaust temperature sensors are sometimes called. We'll let that run continue on to the other side. We're going to have an output called R pyro temperature. Notice there's an R there. We haven't done that before. And that means a data type of type real. So this might tell you that you're 800 degrees or that you're 70 degrees or something like that. It'll give you an actual value. We'll come back to that quite soon in this class. Over here, we have an input going to this function block. We'll let that be an unsigned integer, pyro, actually pyro1. So that's a 1. And we'll also have something over here, a type real for high temp. So what this does, it's an input, it's a type real that goes into the function block. The function block inside makes a comparison. It's looking at the raw data coming in, and it's looking at the temperature. And if the temperature is too high, it'll come over here, and it'll set the lever to either true or false. And then you have something out here called, or a coil I should say, called Boolean pyro 1 over temp. And I know I've mentioned these user-defined function blocks before, but you're starting to see the utility they have. Again, this is something I don't want to deal with today. What I can tell you is that we can take an analog sensor, we can get it into the PLC, and we can make some comparisons, and we can have something that tells us that this particular analog sensor has a value that is too high. As far as our logic is concerned, we are going to say ... that there are 4 of these, 1 for pyro 2, pyro 3, and pyro 4. And now I'll tell you the objective. We want to have a lamp over here that will activate when any of those exhaust temperatures are too high. So pyro 1, 2, 3, 4. If any of these is too high, maybe we want a lamp here that says over temp. Okay, so over temp. So we come down here, Boolean over temp, and we'll let that accept this pyro here. Pyro run over temp. Pyro 2, 3, and 4. We OR them all together, and we are done. So that is a logic OR. So if any of these activate, we will have an over temperature lamp. Have some parting thoughts. Focus. Focus on one thing at a time. That's rung by rung. It's tabular. Several times you saw me do this, where we talked about an input. Right? We gathered all the inputs in one location. We gathered all the outputs. Right? So there are several inputs, several outputs, and then you described a behavior. Okay, that's an important consideration. You can do that as a rung by rung. That might be useful at first, so you can capture everything. For example, at one point we had a rung with 6 inputs, and that gets a little tricky. But again, you identify the behaviors and you keep working at it. You could also use this to describe the entire machine, if you like, as well. The last thing I described was the user-defined function block. And part of me says, well, that's just magic. The other part of it says it's an extremely useful mental device that you can use. Because you can say, I have some function, and I'm not sure exactly how to build it yet, but I know that it must do these things. So maybe you put it aside, maybe you put it into tabular form, and you say, this is what my user-defined function block does. And you're not sure exactly what it is, but you know it has an output or an input, and that allows you to think through the rest of the circuit. As we conclude, I'd like to leave one final tip. I mean, obviously is experience. The more you code, the better you get at it. The other is iteration. When you first start coding, it looks something like this. You're on a path, and you think you're on a good path, or you could have taken that path, or maybe you took this path. And you never know when you're first starting out if you're on a good path, because you just don't have the experience yet. And sometimes it works out that this is a very bad path. There is no success there. Maybe this one's bad as well. This is the path you might need to take. And what's really unfortunate is that people take these bad paths and they hit this brick wall and they refuse to start over again. Sometimes it's better just to scratch this entire thing, go right back to the beginning, and start over again. But this time, the difference is you know a little bit more about the code, and you also know a little bit more about what your code is supposed to do. Right? So as an iterative process, sometimes you have to come back and in tabular form, write down what your behaviors are, or maybe capture another input or output that you missed. That's it for now, folks. When you come back next time, we'll talk about circuits with memory. In particular, we'll talk about the seal-in circuits, the latch circuits, and just touch on things that are sequential, where one event happens after another.